All right, so today we were taking a deep dive into the world of helicopters.
These iconic machines we all recognize. But I have to admit, before we got started today, my knowledge was pretty much limited to they spin, they fly, they're loud.
Well, get ready to have your perspective shifted
There's a
because
lot more to these whirly birds than meets the eye.
that's what I like to hear. So let's break it down. Technically speaking, when we talk about helicopters, we're talking about rotorcraft.
Exactly. And what sets them apart is their ability to generate both lift and thrust from those massive, horizontally spinning rotors.
That's what gives them the almost magical ability to take off and land vertically, hover in midair, and even fly backwards, things most other aircraft just can't do.
It's true. Those capabilities open up a world of possibilities, from navigating dense jungles to landing on skyscrapers. But before we get too far ahead of ourselves, something I've always wondered. What's the difference between a helicopter and an autogyro? They both have rotors, right?
You're right, they both have rotors, but the key difference is how those rotors are powered. In a helicopter, the engine directly powers the rotors, giving the pilot much more control over the amount of lift generated.
In an autogyro, on the other hand, the rotor is free spinning for at least part of the flight, relying on airflow as the autogyro moves forward to generate lift.
So with a helicopter, it's all about that direct control, which explains those impressive hovering skills we see in action movies and rescue missions. Now, speaking of rotors, there are a surprising number of configurations out there.
You're not kidding.
We're most familiar with the classic single main rotor and tail rotor setup, but you've also got tandem rotors, coaxial rotors, and even the quadcopters we see on drones nowadays.
It really highlights how far helicopter design has come. For instance, did you know the first helicopter to reach full-scale production was the Sikorsky R-4 all the way back in 1942? That's not that long after the Wright brothers at Kitty Hawk.
It's remarkable, isn't it?
It speaks volumes about the ingenuity of those early engineers, especially considering the technological limitations they faced.
Speaking of ingenuity, I'm dying to know, how do these things actually fly? What's the secret sauce that allows a helicopter to defy gravity?
It seems impossible.
It's a question that's puzzled even the brightest minds for centuries, and the answer might surprise you with its elegance. It all boils down to those spinning rotors and their cleverly designed blades. Think of each rotor blade as a mini-wing, an airfoil, just like on an airplane.
As the rotors spin, these airfoils slice through the air, creating a difference in pressure, higher pressure below the blades and lower pressure above.
That pressure difference generates lift, enough to heave the entire helicopter skyward.
So it's all about manipulating air pressure. It's like those giant fans they have at sporting events that can practically blow you over if you get too close.
That's a great analogy.
Now, here's where the engineering gets really ingenious. Spinning those rotors at such high speeds generates a tremendous amount of torque, a twisting force that would send the helicopter spinning wildly out of control in the opposite direction.
Oh, right. Like when you were a kid playing with toy helicopters and they'd want to twist in your hand when you rev them up.
Exactly. To combat that torque, most helicopters utilize a tail rotor, that smaller vertical rotor you see on the tail boom.
It provides a horizontal thrust in the opposite direction of the torque, keeping the helicopter stable and pointing in the right direction.
It's like a counterbalance, a delicate dance between opposing forces. But I'm guessing the tail rotor isn't the only way to solve this engineering puzzle, is it?
You're right. There are some fascinating alternatives out there. Some helicopters, like those with the fenestron or fantail designs, employ ducted fans for this purpose.
These are essentially fans enclosed within the tail boom, offering a quieter and often more aerodynamically efficient solution.
Quieter operation would certainly be appreciated by anyone living near a helipad.
Absolutely. Then you've got the NOTAR system, a true testament to out-of-the-box thinking.
Instead of a separate rotor, it cleverly utilizes the Coanda effect, directing a jet of air along the tail boom and using the surrounding airflow to create a sort of virtual tail rotor.
Well, that's thinking outside the box.
Yeah.
It makes you appreciate the constant innovation happening in helicopter design. Now, we've talked about lift and counteracting torque, but all of that requires some serious power. What can you tell us about the engines that make these incredible machines soar?
That's a story in itself. Early attempts at helicopter engines were, shall we say, limited by the physics of the time.
I'm picturing something like Leonardo da Vinci sketching out a helicopter powered by steam.
Not quite, but you're not far off. Early pioneers experimented with everything from steam engines to those clunky internal combustion engines used in early automobiles. While they provided more power, they were often heavy and unreliable, severely limiting helicopter size and performance.
Sounds like it was a constant battle to find the perfect balance between power and weight.
Exactly. And then came the game changer, the turboshaft engine.
First introduced in the early 1950s, these engines offered a remarkable power-to-weight ratio. They were more compact, lighter, and far more reliable than their predecessors, paving the way for the larger, faster, and more capable helicopters we see today.
So the turboshaft engine was a pivotal moment in helicopter evolution. It's like the difference between the first clunky computers and the sleek smartphones we carry in our pockets today.
A very apt comparison.
It's amazing to think that most of the helicopters gracing our skies today owe their existence to this revolutionary engine.
Okay, so we've got these amazing machines powered by incredible engines. But I have to ask, how does one actually fly a helicopter? It seems so much more complex than flying a plane with all those rotors and controls.
You're right, piloting a helicopter requires a different skill set than flying a fixed-wing aircraft.
It's all about coordination, especially when it comes to hovering, which is one of the most challenging aspects of helicopter flight.
What makes hovering so tricky?
Imagine trying to balance a basketball on your fingertip while standing on a moving platform. That's kind of what it's like to hover a helicopter. You're constantly battling the wind generated by those massive rotors, making minute adjustments to the controls to maintain a stable position.
It sounds nerve-wracking.
It can be, but that's where the pilot's skill and the helicopter's ingenious control system come in.
Speaking of control systems, I've always been curious about all those sticks and pedals in a helicopter cockpit. How do they work together to maneuver these machines in 3 dimensions?
Let's break down these controls, starting with the cyclic that's stick-like control, usually positioned between the pilot's legs.
So the cyclic is what gives the pilot directional control.
Precisely. It controls the helicopter's movement in the horizontal plane, forward, backward, and side to side.
Think of it like the joystick on a video game. Pushing it forward tilts the rotor disc forward, moving the helicopter forward. Pulling it back has the opposite effect. Moving it left or right makes the helicopter move sideways.
So the cyclic is like the steering wheel of the helicopter, dictating its horizontal movement. What about altitude? How do pilots control whether they climb, descend, or hover?
That's where the collective comes in, which is that lever usually located on the pilot's left side.
It controls the pitch of all the main rotor blades simultaneously. Pulling up on the collective increases the pitch, generating more lift and causing the helicopter to ascend. Pushing it down decreases the pitch, reducing lift and initiating a descent.
So it's like the throttle in an airplane managing the helicopter's vertical movement. We've got the cyclic for horizontal control, the collective for vertical control. What about those pedals down there?
Those are the anti-torque pedals, and they're crucial for controlling yaw.
Yeah.
Essentially, it's the helicopter's rotation around its vertical axis. Think of it like turning your head left or right.
These pedals control the pitch of the tail rotor blades, which in turn controls that rotation, allowing the pilot to point the helicopter's nose in the desired direction.
So the pedals are like the rudder on a boat, keeping the helicopter pointed in the right direction. It's incredible how all these controls work together, allowing skilled pilots to maneuver these machines with such precision.
It's a testament to both human ingenuity and the countless hours of training those pilots undergo to master these complex machines.
It really makes you appreciate the skill involved.
Absolutely. And it gets even more impressive when you consider the 3 basic flight conditions a helicopter pilot must master: hover, forward flight, and the often tricky transition between them.
Let's start with hover. What makes it such a challenging maneuver to master? Let's start with hover. What makes it such a challenging maneuver to master?
Well, it's all about finding that sweet spot, that perfect equilibrium where lift and thrust and gravity are all in perfect harmony.
Too much lift and you're shooting skyward. Too little and you're headed back down.
And the wind, the wind is constantly trying to throw you off balance. It's a constant dance of adjustments, using all 3 controls, cyclic, collective, and pedals to maintain that delicate balance.
So it really is like balancing a basketball on your fingertip while standing on a moving platform, like you said earlier.
The perfect analogy. It requires incredible finesse and constant attention.
Okay, I'm starting to understand why they say helicopters want to be in motion. What happens when you transition from a hover to forward flight?
That's when things get a bit smoother, actually. Once a helicopter gains enough speed, usually around 16-24 knots.
Something interesting happens. It experiences what's called translational lift. Essentially, as the helicopter moves forward, the airflow over the rotors becomes more horizontal, providing an extra boost of lift without the pilot needing to increase power.
So it's like the helicopter's catching a break from physics for a moment.
In a way, yes. This translational lift makes that transition from a hover to forward flight much smoother. And once in forward flight, the controls behave a bit more like those of an airplane. The cyclic controls the pitch, the collective manages power and altitude, and the pedals maintain balanced flight.
So it's a delicate dance at low speeds. Then it becomes a bit more like flying a plane at higher speeds.
You got it. And mastering that entire spectrum, from a dead-stop hover to high-speed flight, is what makes a truly skilled helicopter pilot.
Okay, so we've covered how to fly these things, but let's talk about why it all matters.
Sure, helicopters are marvels of engineering, but how are they actually used in the real world?
Where do we even begin? The versatility of helicopters is astounding. They can access places other aircraft can only dream of: dense jungles, mountaintops, even bustling cityscapes.
It's true. I've always been fascinated by those massive helicopters used in construction, the ones that can lift ridiculously heavy objects with what looks like effortless grace.
Those are called aerial cranes, and they're the heavy lifters of the helicopter world, capable of placing equipment on skyscrapers, transporting massive air conditioning units, even airlifting entire prefabricated buildings with incredible precision.
It's like something straight out of a sci-fi movie.
Speaking of sci-fi, did you know that NASA developed a helicopter called Ingenuity to explore the surface of Mars?
It's already wrapping up its mission, and the data it collected is incredible. It proved that flight on another planet is not only possible, but achievable with today's technology.
That's pushing the boundaries of what's possible.
And it speaks volumes about the potential of helicopters, both here on Earth and beyond. But you're right, they're not just for high-tech exploration or Hollywood stunts. Helicopters play a critical role in countless industries and everyday situations.
Like emergency services. I can't imagine a world without medevac helicopters or search and rescue teams relying on these machines to reach remote or hazardous locations.
Absolutely, they're lifesavers, literally. And let's not forget their role in firefighting, especially battling those massive wildfires we've been seeing more and more of. Helicopters equipped with those giant Bambi buckets can drop thousands of gallons of water or fire retardant with pinpoint accuracy, while others transport firefighters and equipment to areas inaccessible by ground vehicles.
It's incredible how many lives are saved, thanks to these machines. What other surprising uses might people not even think about?
Oh, there are so many. Farmers use them for crop dusting. Tourists take breathtaking sightseeing tours. News crews rely on them for aerial footage. Even law enforcement agencies utilize them for surveillance and pursuit.
It sounds like there's a helicopter for every occasion.
But they're not without their risks, are they? I imagine flying one of these things, especially in challenging conditions, is inherently dangerous.
You're right, despite all the technological advances, helicopter flight has its inherent risks.
What are some of the hazards pilots have to be constantly aware of? I'd imagine weather plays a huge role.
Weather is a major factor, but there are other, less obvious dangers. For instance, unlike airplanes, helicopters have a maximum speed limit beyond which things get very hairy very quickly.
Wait, why can't helicopters just keep going faster and faster?
It all comes down to how those rotors generate lift.
As a helicopter accelerates, the advancing rotor blade, the one spinning in the direction of flight, starts moving through the air at increasingly higher speeds, relative to the retreating blade.
If the helicopter goes too fast, that advancing blade can actually approach the speed of sound.
Supersonic rotor blades. That doesn't sound good.
It's not good at all. It creates a dangerous amount of drag and vibration, placing enormous stress on the rotor system. And even before that happens, the retreating blade, now moving much slower through the air, can lose lift and stall, leading to a sudden loss of control.
So it's all about maintaining that delicate balance between the forces acting on the advancing and retreating blades.
Precisely. Push too far in either direction, and things can go wrong very quickly.
You mentioned vibration. That's another hazard that always comes to mind when I think about helicopters.
It's a constant concern. Helicopters, by their very nature, generate a lot of noise and vibration, and prolonged exposure can lead to fatigue, discomfort, and even long-term health problems for pilots.
Well, I imagine it's like being strapped to a giant vibrating machine gun.
That's one way to put it. But it's not just about comfort. Excessive vibration can also wreak havoc on the helicopter itself, putting stress on the airframe, the rotors, and especially the transmission, which is one of the most critical and complex components of a helicopter.
So how do engineers combat these vibrations?
It's a constant area of research and innovation, but some common techniques include incorporating vibration dampeners into the design, carefully balancing the rotors to minimize vibrations at the source, and using advanced materials that can better withstand those constant stresses and strains.
It's incredible how much thought and engineering goes into mitigating these hazards and making helicopters as safe as possible.
Absolutely. And then there are the more situational dangers, like loss of tail rotor effectiveness, where the airflow from the main rotors disrupts the tail rotor's ability to function properly, leading to a loss of control.
So the very thing that keeps the helicopter stable can sometimes be compromised.
Exactly. And then there are dangerous situations like settling with power or vortex ring state, where the helicopter descends too rapidly within its own downwash of air, making it incredibly difficult to recover.
It sounds like helicopter pilots need nerves of steel.
You could say that. They're constantly juggling these potential hazards, all while maintaining control of a complex machine in a constantly changing environment. It's a true testament to their skill, training, and composure under pressure.
Well, I have to say, this deep dive has given me a newfound appreciation for helicopters. What started as simple curiosity has turned into a fascinating journey through the mechanics, history, uses, and even the hidden dangers of these remarkable machines.
It's been my pleasure to guide you on this journey. Helicopters often get overshadowed by their fixed-wing cousins, but as you've discovered, they're incredible feats of engineering with a rich history and a bright future.
Absolutely. Yeah. So the next time you hear that distinctive thwop, thwop, thwop of a helicopter overhead, take a moment to appreciate the symphony of forces at play, the skill of the pilot at the controls, and the countless ways these machines impact our lives, often in ways we rarely even consider.
Well said. Well said.
This has been The Deep Dive. Until next time, keep exploring, keep questioning, and never lose your sense of wonder.